will estimate population mean. So if you remember, a point estimate is a single value or point used to approximate a population parameter. The parameter we're trying to estimate now is the population mean, mu. The best the best point estimate for the population mean, mu, is the sample mean x bar. So the sample mean x bar is the best point estimate of the population mean. We mentioned that when we were looking at population proportions. All right, now for all of these confidence intervals that we're going to be doing, what we're really doing is we're taking the point estimate and we're adding something to it and we're subtracting something from it. Now that number that we're adding to and subtracting from the point estimate is the margin of error. Now in this case, the point estimate is going to, in the last section, the point estimate was p hat, and we added and subtracted a margin of error that was, we had a formula for in the last section. In this section, we are going to use the point estimate x bar, and we're going to get a different formula for E. So the plus or minus E here is plus or minus a different margin of error. So we have a different point estimate and a different margin of error for each one of the interval estimates that we do. So in the section on proportions, we use p hat, and the margin of error was equal to the z of alpha over 2 times the square root of p hat times q hat over n, remember? But in this section, we're using a different margin of error because we're estimating a different population parameter. We're estimating mu. So in this case, our E is not going to be the E that we use for proportion. That's the E we use for proportion. In our case, our margin of error now is going to equal the critical value, z of alpha over 2, so that's common to both. But now, instead of multiplying by the square root of p hat times q hat over n, we're multiplying by sigma over the square root of n. And sigma over the square root of n, if you remember, was the central limit theorem, not variance, standard deviation. So this is the standard deviation of a sampling distribution. So for all of these, what we're going to be doing is multiplying the critical value by the standard deviation, but the standard deviation is coming from various places, and the critical value is coming from various places. For instance, this would be the standard deviation if it were applied of a single binomial trial, and this is the standard deviation that we get from the central limit theorem. All right, so that's what we're going to be doing. We're going to be finding point estimates and adding and subtracting some margin of error. So here's the confidence interval estimate, and we have a different way of calculating the margin of error, not only based on what parameter we're aiming for, but also based on whether we know the population standard deviation or not. If we know the population standard deviation, then we're going to use this margin of error right here. And if we don't know the population standard deviation, we're actually going to find the margin of error in a different way that we're going to look at in the next section. All right, so for now, we're going to be using this margin of error, and we're going to be creating a confidence interval using this margin of error and the point estimate x bar. Okay, so there are certain requirements and notations that we're going to look at. The notation that we're looking at is mu for the population mean. We have sigma for the population standard deviation. X bar is, of course, the sample mean. N is the number of sample values, or the sample size. E, once again, is the margin of error, which is the maximum likely distance from the point estimate to the population parameter. So in this case, it's the maximum likely distance from the point estimate x bar to the population parameter mu. So it's the maximum likely distance for that difference. The z of alpha over 2, well, that's still our critical value, which is the right tail of the standard normal distribution having alpha over 2. So that's still the same. All right, now the requirements. The requirements are important. The first requirement is that the sample is a simple random sample. Well, we have no way of verifying that. They have to tell you whether or not the sample was a simple random sample. So that requirement is going to be met by you being told that it's met. Number two, the value of the population standard deviation is known. Well, that's something that you either know that you have. It either says that the population standard deviation is this number, or they'll give you a sample standard deviation. So if you know the population standard deviation, we can actually use the method of this section, because you have to know the population standard deviation here. If you don't know the population standard deviation, then we can't do the problem. We can't create the confidence interval with the method of this section. The third requirement is really the most important requirement. The third requirement is the one that you actually have to check. The third requirement is that either or both of these conditions are satisfied. Either the population is normally distributed, or you have a large enough sample. And by large enough sample, we mean that the sample size is greater than 30. All right? So this is how we're going to create our confidence interval. We're going to use this margin of error, and we're going to take x bar and add the margin of error to it and subtract the margin of error from it, and we're going to create an interval in that way. But before you can actually start creating intervals, you have to be able to verify that you can actually use this margin of error by going through these three requirements and making sure that they're all met. So let's take a look at this example. All right, in this example, it says, in exercise 9 through 12, find the margin of error of the confidence interval if the necessary requirements are satisfied. If the requirements are not satisfied, state that the margin of error and confidence interval cannot be calculated using the methods of this section. So if we don't meet those requirements, we can't use the methods from this section to calculate the confidence interval. So let's go ahead and see if we meet the requirements for number 10. So for number 10, let's see what we have. Braking distance. The braking distance of a simple random sample of cars. So we have a 95% confidence level. So my confidence level is 0.95, 95% confidence level. And we have a sample size of 32. So n is equal to 32. And they also give us x bar. X bar is 137 feet. And it says that sigma is known. So we know that sigma is equal to 7 feet. So let's see if we meet all the requirements first. Like I said, the requirement that the sample be simple random, a simple random sample requirement, well, that you have to be told whether the sample is a simple random sample, because you're not the one collecting the sample. Part 2, the value of the population standard deviation is known. It says right here, sigma is known, and it's 7. So requirement 2 is met. And requirement 3, either or both of these conditions is satisfied. Either the population is normally distributed. Well, I don't see anything here that says the population is normally distributed, but let's see the other condition. Or n is greater than 30. Well, here's my sample size n, and n is 32, which is a larger number than 30. We don't actually have to meet both of these requirements or both of these conditions. We only have to satisfy one. That's why it says either or both. So we've met the requirements. All three of the requirements are met because n is greater than 30. The population standard deviation is known to be 7, and this is a simple random sample. So now we can actually go ahead and calculate the margin of error. So let's go ahead and do that. Now the margin of error. To calculate the margin of error, there are things that I have to know. I have to first know the critical z value. I know sigma and I know n, so the only thing I really have to calculate here is the critical z value. To calculate the critical z value, I have to know alpha, and alpha is 1 minus my confidence level. So let's find alpha is equal to 1 minus the confidence level, and the confidence level here is 0.95, so that alpha is 0.05. And what I want to do is I want to find the z-score that separates an area of alpha over 2 in the right tail of the standard normal distribution. So we have the standard normal distribution. I want to have an area of alpha over 2 over here in the right tail. Well, alpha over 2 is half of 0.05, which is 0.025. So I want an area of 0.025 in the right tail, and I want the z-score that separates that area. So when I'm doing this on the calculator, I'm actually going to have to put in 1 minus 0.025, because the calculator will only take the area to the left of the z in the inverse normal function. So Let's go ahead and do that. Let's see. We have, oh, oops. All right, so in the TI-83, what we're going to do, well, let's clear it first. We're going to go to second. We're going to go to distributions, and we're doing the inverse normal distribution. So we go down to number 3, and we're finding the inverse norm of 1 minus 0.02. Oops, I didn't do the 1 minus. It's 1 minus 0.025, and we press enter, and we get the z score is 1.96. So my critical z, my z of alpha over 2, is equal to 1.96. Let's clean that up a little bit. So we have the z score that I need here. The z of alpha over 2 is equal to 1.96, and we already knew that sigma was equal to 7. So now we have all the information we need to calculate our margin of error. The margin of error is going to be the z of alpha over 2. The z of alpha over 2, we already said, was the number 1.96. We just found that. And we're going to multiply that by sigma, which is 7, over the square root of n, which is over the square root of 32. So we're going to do this calculation, and this calculation is going to give us our margin of error. So let's go ahead and do that. All right, so let's see. The margin of error is then going to be equal to, let's bring out our trusty calculator here. Let's see, our margin of error is going to be, turn it on, clear, 1.96 times, and then I have 7 divided by the square root of 32, close the parenthesis, and this gives us 2.43. 2.43. So let me see here. Let's see where what x bar looks like. X bar is 137. So I want to round my margin of error so that it has the same number of decimal places as x bar. So I'm going to round this to approximately 2 being my margin of error. So now I've calculated my margin of error for number 10. So the requirements were met, and once I realized that the requirements are all satisfied, I used the method of this section in order to find the margin of error. Let's take a look at number 12. Let's take a look at problem number 12. The answer for number 10 is 2, though. The margin of error is 2. So let's take a look at number 12. Number 12 is here. And number 12 says failure times. The times before failure of integrated circuits used in calculators, and that's what we're going to create a confidence interval for if we can use the method of this section. Let's see what we have. We have 99% confidence. That is the confidence level. You need the confidence level in order to calculate alpha. So the confidence level is 99%, 0.99. We have n. It gives us n is equal to 25. We also have x bar. X bar equals 112. And then it says sigma is known. So sigma is known, is given, and sigma is known to be 18.6 hours. And the distribution of all times before failure is far from normal. So this is not a normal distribution. So let's go through our requirements to see if we can actually apply the method from this section that we just used to get the margin of error for number 10. First, the sample is a simple random sample. Well, you can always, in general, that requirement should be met. Simple random sample. You cannot answer that question on your own. That has to be given because you didn't take the sample. Number 2, the value of the population standard deviation, sigma, is known. Well, here it is. Sigma is 18.6, it says. And it says right here, sigma is known. That phrase actually appears in the question itself. Number 3, this is the one, like I said, that's the most important one. This is the one that you have to check most of the time. Either or both of these conditions is satisfied. So we only have to meet one of these conditions, but meeting both is fine also. The population is normally distributed. it says here the population is far from normal, so that condition is not met. But we can also meet the other condition and still use the method of dissection. So let's see if we meet the other condition. The other condition is that n is greater than 30. Well, our n is 25, which is not greater than 30. So in this section, or sorry, for this problem, we cannot use the method of dissection because we don't meet all the requirements. Let's see, which requirement is not met? We don't meet requirement number 3. Requirement number 3 is not met. Requirement number 3 not met. And the reason why requirement 3 is not met is because this is not a normal distribution. It says it's far from normal, as a matter of fact. And n is only 25, which is a smaller number than 30. So we haven't met requirement 3. Therefore, we have to say that the margin of error and confidence interval cannot be calculated using the method of dissection. So that's how we do number 12. We can't do it with the methods of dissection. Let's take a look at number 22 and see if we can actually calculate a confidence interval instead of just finding a margin of error. Actually, because we found a margin of error here, we could have actually done the confidence interval for this one. So let's actually do a confidence interval for number 10. So we know that number 12, the requirements were not met. So let's get rid of number 12. And let's actually make a confidence interval for number 10. So let's make a confidence interval for number 10. For number 10, we have that x bar is equal to 137. And we also have that E we just found from when we did this problem previously. We found that E was 2. So my confidence interval is going to be the point estimate, x bar in this case, plus or minus the margin of error, E. In this case, we have 137 plus or minus 2. So we're creating a confidence interval here. And the confidence interval, the lower limit, is 137 minus 2, which is 135. And the upper limit is 137 plus 2, which is 139. So this would be a confidence interval estimate for the true braking distance let's see, this is measured in feet. So the true braking distance for this car or these cars is somewhere on the interval from 135 to 139 with 95% confidence. All right, so that's how we would do a confidence interval by hand. To do a confidence interval by hand, we find the point estimate, we find E, and then we add and subtract E to the point estimate. Now we'll do a confidence interval using our TI-83 calculator, okay? So let's take a look at this number 22, NCAA football coach salaries. A simple random sample of 40 salaries of NCAA football coaches has a mean of 415,953. Assume that sigma is equal to 463,364. So they're telling us sigma. The fact that they use the symbol sigma means they're giving us the population standard deviation. They don't have to say it explicitly, but if they use the symbol sigma, automatically is the population standard deviation. Part A says find the best point estimate for the mean salary of all NCAA coaches. Well, that's a simple one. The best point estimate for a population mean is the sample mean. And here we have a sample of 40 coaches, that has a mean of 415,953. So X bar is actually the best point estimate, and X bar in this case for this sample of 40 salaries is 415,953. So that's going to be the best point estimate, X bar, which comes from these 40 salaries. Part B, construct a 95% confidence interval estimate of the mean salary of an NCAA football coach. Well, for this, we're going to use our TI-83 calculator. So let's pull that out here. And let's turn it on and clear it. Okay, now in this case, what we're going to do is we're going to go to Stat. And under Stat, we're going to go over to Tests. And there are a bunch of tests here. And when we were doing proportions, we did a one prop z int. Now what we're going to do is we're just going to do number 7 because we're doing just a z interval. So we're doing number 7, which is the z interval. So we press enter. And then it's going to ask me whether I have data or statistics. In our case, we don't have raw data. What we have is statistics. So I'm going to go over and I'm going to highlight that we have statistics. If we had raw data, it would ask us where the data was. It would be in one of our lists, and we would do it that way. But in this case, we have statistics. So I highlight statistics and I go down. It asks me for those statistics now. It's asking me for sigma. Well, sigma was given up here. Here's sigma right here. So sigma is the number 460. Oops, sigma. Where did I get 7? 463,364. So that's my sigma, 463,364. My x bar, well, x bar is 415,953. And my value of n, well, that's the number of points in my sample, the number of data values in my sample, and that's 40. See the sample size here, n is 40. So I have 40 football coach salaries, so n is equal to 40. And then the confidence level is 95%, so this is all right. We have 95% already. Then we go to calculate. When we hit calculate, it gives us our interval estimate. So it says here, let's see here. It says here that let's go back. It says here that our interval estimate is, the lower limit is 272,358. So the interval starts at 272,358. And the upper limit of our interval is 559,548. So 559,548. So here I have my upper and lower limits of my confidence interval. This produces the same number as if I found the margin of error and added that number and subtracted that number from x bar. So now for part C. Part C says, does the confidence interval contain the actual mean of 474,477? And yes, it does. That number falls in the range from this to this. That number is actually captured. So the answer for part C is yes. That interval does actually contain the true population mean. All right, now let's talk about finding sample size. Now we did this also for proportions. And what happens is, we don't know a population parameter, but we want to estimate it with a sample. Well, we're going to go out and we're going to take a sample of n things to find out what our estimate is. But how do you know how many people to survey or how many things that you need to have in your sample? Well, there's actually a required sample size for you to get a correct estimate. And this is how we're going to find that required sample size. So the objective here is to determine how large a sample should be in order to estimate the population mean. Before, we looked at how large a sample should be to estimate the population proportion, P. Now, the notations are all the same here. And here's the formula that we're going to use in order to find n. All right, so that is what the most important thing is, the formula for finding n. So let's take a look at number 32. Number 32 says, sample size for white blood cell count. What sample size is needed to estimate the mean white blood cell count for the population of adults in the United States? Assume that you want a 99% confidence. So that's my confidence level is equal to 0.99, 99%. You assume that you want a 99% confidence that the sample mean is within 0.2 of the population mean. So within 0.2 of the population mean. Last time we did this, we saw that kind of phrase also. And then when it said within a certain number, we said that was actually, we were actually being given E, the margin of error. It's the same thing here. However many you want to be within of the actual mean, population mean, is the margin of error. It's the distance from the population mean, or the maximum likely distance from the population mean. So this actually is E. They're telling us here that E is equal to 0.2, the margin of error. So we have the confidence level, we have the margin of error, and let's see what else we have. The population standard deviation, so they're also giving us sigma. They're telling us sigma is equal to 2.5. So we have everything we need to calculate n, except for the z of alpha over 2. To find the z of alpha over 2, we need alpha. Alpha is 1 minus the confidence level, which is 1 minus 0.99, and that's equal to 0.01. And what we need the z-score that separates alpha over 2 in the right tail. So we want an area of alpha over 2 in the right tail. Well, half of this is 0.005. That's half of alpha. And I need this z-score that separates 0.005 in the right tail of the standard normal distribution. So let's go ahead and find that number, the z of 0.005, that critical value. So our calculator, we go to that. And once again, we're going to the inverse normal function. So to do second, we go to distributions. We're doing number 3, the inverse normal. And then we're plugging in actually the area to the left, which is 1 minus, oops, not times, 1 minus 0.005, which is 2.58. So this is equal to 2.58. So now what we're going to do is we're going to go ahead and we're going to find n with all of these numbers. Well, it says n is equal to, and then all of this goes in a bracket, and it's all being squared, the z of alpha over 2, which is 2.58 we just calculated, 2.58, times sigma. Well, sigma we found was 2.5, 2.5, all divided by the margin of error, which is 0.2 squared. So we're going to square all of this. So let's go ahead and do that calculation and find our margin of error, or sorry, our sample size, our required sample size, n. So let's see. Let's go back to our TI, and we're doing this calculation. We're doing 2.58. Oops, there's some more space here. We're doing parentheses. Oops, let's turn it on first, right? We're doing our parentheses. 2.58 times 2.5 divided by 0.2. Close that parenthesis, and we're raising this entire thing to the second power. We press enter. And remember, we always round this up. So since we have a fraction, we have a decimal here, we're going to raise this, we're going to round this up to 1041. 1041. And that's how we determine what sample size we need to estimate a population mean.